Well, thanks everybody for joining. My name is Brett Quinn. I work in PowerMax Mainframe Engineering. This October will be 30 years with EMC, now Dell. And most of that time has been focused on advanced business continuity solutions in the mainframe space. So what we're going to talk today about is ransomware protection for your mainframe data. And this will focus on Dell Technologies offerings in this area, mostly for DASD, but we'll talk about tape a little bit as well. And this is a precursor to a demonstration, which will be the next session after this one, done by Gary Smoke from Dell. So I think we all know what the threats are and why we're talking about ransomware protection and cybersecurity and cyber resiliency. This is data from Cybersecurity Ventures and also Accenture, showing the frequency of attacks and the cost of those attacks and the average cost of those attacks by industry. And this data is a few years old. So I think the common knowledge is that this is only getting worse, and we need to provide some method of protection as well as recovery and also detection. And I will talk about all three of those things. The way we talk about it is in the NIST framework, which I'll talk about. But why do we need to talk about this at all, and why cyber resiliency for the mainframe? It's because really cyber resiliency and cyber recovery as a component of resiliency is the next wave of business continuity planning. Really, you need to look at recovery plans to include the ability to eliminate the risk of data loss from undetected intrusion and data destruction. So it's not just DR anymore. The threat has expanded beyond DR to intentional data corruption or destruction, and resiliency, cyber resiliency must ensure that you have solutions in these areas. And this table kind of, compares and contrasts what's different between cyber resiliency and disaster recovery. The recovery time, recovery point objectives are, of course, a little bit different, and the focus and impact of the disaster is generally data focused as opposed to physical. We're focused on the loss of the integrity of data rather than the loss of the data resources. So there's a difference there. We'll kind of walk through that. It's a very different mindset. And I'm hoping that the industry will come to a solution for this much more quickly than it did took about 10 years or 15 years really to get from 2-site synchronous replication to 4-site replication, which is where we are now. Hopefully it will take 15 years to resolve the cyber resiliency problem. We do see that many users are building separate cyber vaults, and these cyber vaults can be virtual or physical. Often they're deployed at the disaster recovery site. And I'm going to go through some examples of how Dell customers have done that using Dell technology. But the framework against which we measure these requirements is the National Institute for Standards Cybersecurity Framework, which has become the de facto standard. DORA has in the EU has also adopted these 5 pillars of identify, protect, detect, respond, and recover as the elements of the cybersecurity framework. And we'll talk about these elements with regard to how Dell is providing functionality to address them. First in the protect pillar with Dell's ZDP solution, Data Protector for Z Systems. And then also on the recover side, how ZDP can be used to recover these from these attacks. But the most important area of growth, I think, is in the middle, which is detection. And I'm going to talk about that after we cover the first two. So the basic requirements for ransomware protection from a data storage point of view are isolation, separating the data physically and logically, immutability, a key attribute to preserve the data integrity by ensuring that it cannot be altered when you make a point-in-time copy of the data for recovery purposes, cannot be altered, and also it cannot be terminated prior to its expiration date. So not being able to delete it is just as important as not being able to alter it. And we'll talk about this notion of secure snaps as we go along. And finally, intelligence. This is the area that we're going to see a lot of growth in with regard to the detect pillar in the cybersecurity framework. Customers are increasingly asking their vendors, both software and hardware vendors, can you tell us when the data has been compromised from an integrity point of view, whether it's encryption or just exfiltration, right? Exfiltration is as much a threat as data destruction, right? The theft of data. So how do we make sure that we identify when something's going wrong? And machine learning, artificial intelligence, analytics are ways to do that. And we have some solutions that we've introduced in this area. And we'll talk about that as well. So let's just get this concept fundamentally laid out here of physical versus logical recovery. It's really the difference between infrastructure protection and data protection. So in a normal configuration, we're going to show a 3-site topology, very common in large mainframe environments. In fact, we're seeing more growth to 4-site and beyond topologies. But 3 sites is common, continuous availability in one region, region A in this example, with either hyperswap or autoswap, and a recovery site, region B. So it's got 3-site protection from a disaster. You've got high availability within the region and an out-of-region restart capability. And generally, this is wrapped around, with some automation solution like GDPS or GDDR. In our case, it would be GDDR. Now, at the remote site or at the disaster, in the event of a disaster, you have the ability to, of course, recover. And one disaster might be the loss of the actual physical resource, the storage array itself. And if you have that occasion and you have a product called AutoSwap from Dell, you can swap to the other Vicon attached remotely replicated array in a synchronous replication relationship. So you have continuous availability. And of course, if you have a disaster affecting the entire region, you have the ability to do out-of-region restart. So that's disaster recovery, well understood, well known. It's been evolving since the mid to late 1990s and is well practiced today. Let's take a look at logical data protection because it's a bit different. Here we're going to look at the same configuration, 3-site topology. But if you have a corruption of the data written to the primary, some rogue program corrupts the data, maybe it's a bad actor, maybe it's simple operational error, but you've got some logical data corruption affecting the data. Physically, nothing's wrong with the infrastructure of the environment. And of course, storage-based replication in the form of SRDF, for example, will dutifully replicate that corruption very quickly to the synchronous and to the asynchronous target. So we have a bit of a different problem here. We don't have a physical loss of resources. We have all the physical resources, the data centers, the networks, the processors, the storage, everything's running fine and it's okay. But of course, your data is not okay, and it's not okay in every copy that you've created. So we need to find a way to kind of protect against that and provide recovery capability for widespread data integrity loss caused by errant data or a malicious actor. So how have we done this in the past? Well, the ability to do this was there, but it was limited because you had to consume a lot of resources to make copies of the data in a storage array using TimeFinder Clone, for example, from Dell, or Flash Copy from IBM, or Shadow Image from HDS. You might make 1 copy a day in one of these sites. And if you were really robust, you might make 2, giving you maybe 12 hours of data loss if you had to roll back to one of those copies. And it's very resource intensive. You had to have addressability to all of these copies individually and independently. So if you did make 2 copies, you need to have addresses for both of them to be able to access them on the channel. And it's copy-based. There's a lot of data movement going on here to make a copy of this data. And as a result, because it's copy-based, it consumes capacity. So necessarily, by definition, you couldn't make a lot of copies of this. It was prohibitively expensive to do this in prior technology. So what we've seen with cyber recovery is more pressure to make more copies. So if you look for cyber recovery solutions at a storage level, what should you be looking for? What are some important attributes? Well, the first is, of course, trying to get more granular than the 12 or 24 hours we saw on the last slide. You want to be able to tune the snapshot copies that you're able to make in terms of their frequency from anywhere from minutes to hours, and make a large number of them and retain them for several days or potentially weeks. You want to look for the snapshots being standalone so that if something happens to one of the snapshots, it doesn't mean you can't go back to a point in time that would have required that snapshot. They should all be independent from each other. So every single point in time stands alone and is not reliant on any other points in time to create any specific recovery point. And they should, of course, be immutable. You should not be able to access or alter the point in time copy except through some specific means. And when you do make it available for use, You make it available for use in a way that it can't be altered itself, but just another view of it can be altered. And we'll talk about how we do that in the Dell technology solution. And optionally, you should be able to make it securable, meaning that the user interface provided to manage the point-in-time copies cannot execute a delete command to delete it prior to its assigned expiration date. The notion of security of a secure attribute is a very important attribute for cyber recovery solutions, because you're trying to make many point-in-time copies to give you granularity of recovery. You also want to have something that we call two-actor security. Other vendors call it dual control. The ability to protect the solution itself from a privileged insider trying to act maliciously or under duress through coercion to neuter the cyber recovery solution and the point-in-time copies that it makes by removing volumes from the definition of it, changing the frequency of it, or doing other things that would neuter the protection. So you want to ensure that two people are involved in making any changes to the operational environment that is providing the cyber recovery protection. We call that two-actor security, an important attribute to look for. Space efficiency is very important. As I mentioned, it was very expensive, and you really couldn't do this prior to space-efficient point-in-time copies using the older methods on the previous slide. So you want to look for very space-efficient solutions to obviously reduce the cost of the storage. And if you reduce the cost, you can improve both the scale and the depth of protection. You want to look for solutions that leverage a common pool of storage to make it easy to use. You don't have to manage separate storage pools just to achieve this. It should all be transparent to the user. The objective here is to make point-in-time copies, make many of them, but don't consume large amounts of capacity to either make them or use them. So that's a very important attribute to look for when evaluating solutions that will allow for cyber recovery from for high-frequency point-in-time copies. And of course, you want to try to minimize the RTO. If you have to go use this, you don't want to have to move a lot of data around to be able to access the data or go hunting and pecking for the good point-in-time copy. You really want to provide access to the data to validate it. And when you do need to go use the data, you don't want to have to do full copies of the data in order to make the point-in-time copy accessible for use. So incremental resynchronization is a key attribute to look for. So how do we solve this problem at Dell? What are our cyber resiliency innovations? Well, we came up with a solution coming up on 10 years ago in the prior version of VMAX called SnapVX, which uses a pointer-based technology to make very space-efficient snapshots in a way that does not impact performance and gives you the ability to make some of them secure and some of them not secure, all while saving space, right? Making many point-in-time copies that don't consume space and don't have the copy on write penalty that often came with making a point-in-time copy. And then when we go to use that snapshot, we have the concept of a linked target. You take the snapshot and you link it to a target volume. And that target volume has pointers to the backend resources that contain that point-in-time version of all the tracks that was captured in the snapshot. You make it available, and that linked target is on the channel and can be used. And if you don't like the point-in-time that you got, you just link another one. You don't need to have multiple sets of linked target volumes that are channel addressable. You really just need one set to be able to do that. So let's look a little deeper how that works. Start to SnapVX, and also its companion product for cyber recovery is targeted a cyber recovery solution called ZDP. We'll talk about both these things. The first SnapVX is our local replication solution in the array, and it's built upon our virtual provisioning capability, where we have the storage capacity structured into a single large pool of data, and the thin devices that are on the channel, 3390 Mod 3s or EAVs or whatever size you make them, that are addressable on the channel, simply point on the back end on a track level, track by track. We don't allocate large chunks of data here. This is on a track by track basis, and you get the image of the data spread across all of the devices in the array. So this is inherently very balanced performing solution because all the resources of the array are brought to bear to support the exported volume that's on the channel. So it's very, very space efficient and is very granular in that the allocation units are a single CKD track for the back end. Now, what you can do with these, with this virtual provisioning, and what was a natural outcome of virtual provisioning, in the way it was implemented in PowerMax and the prior VMAX, was to build something called SnapVX. Now, SnapVX is a solution that uses this track granularity, was really architected to exploit it, to provide a point-in-time snapshot in the native batch utility, up to 256 point-in-time snapshots of the volumes, the source volumes, and make them available to target devices by simply linking and unlinking them. In this example, I show snapshots at 10 and 12 noon, and I can link or unlink one or more target devices to them at will. I could share multiple target devices, for example, having multiple test and dev organizations do iterative destructive testing on different target devices if that's what I wanted to do, all without changing the snapshot. The snapshot never changes. The target device changes, it writes its data to a new area in the storage resource pool. So you have the ability to make many very space efficient point-in-time copies because there's a lot of shared allocation going on in the background, and it's all built on top of virtual provisioning. So our virtual provisioning implementation really made this rather simple for us to do. So what are the real benefits here of this notion of space-efficient snaps to make point-in-time copies? Well, what we've done basically is introduce the notion of a targetless snapshot. When you used point-in-time replication, local replication in prior versions of TimeFinder, you had to have a target device, as I mentioned. That's also true for flash copy and shadow image. You had to have a target device. In this solution, you really don't need a target device. We've separated the creation of the point-in-time from its use. Right? The snapshot creates the point in time, and if you want to use it, you simply link it, and the pointers get allocated to the linked target, and you have the ability to access that point in time. If you don't like the snapshot you got, you link a different one. And we don't move data around to achieve this. We're just moving pointers around. And as I said, there's a lot of shared allocation in the back end. So the snapshots have a user-defined name and version number that have an expiration date assigned to them. And it accesses all the data on the back end through the virtual provisioning implementation. It is immutable by its very nature. The snapshots are not addressable on the channel. You can't access them directly. And if you want, you can optionally mark them as secure. And we'll talk about that farther on in the presentation. So how does this really work? Well, the real benefit here is that we're not really making copies of the data as part of the point-in-time creation. We're just capturing pointers, a set of pointers to the data on the back end. We introduced this notion of redirect on write. So when you make a snapshot, the virtual provisioning pointers are captured to create that point in time and point to the same area on the back end that the source device does. And as I said, you can make up to 256 in the batch utility, but in our ZDP solution, which I'll talk about in a minute, you can make up to 1,024 copies of the data. And these point-in-time images are not really physical copies, of course. They're just captures of the pointers and the data structures in the array. And they to all share allocations on the back end pointing to the same point in time. And when a new write comes into the source volume, what actually happens is that's written to a new area of the back end storage resource pool, and the pointer for the source volume is updated. But the snapshots point to the original back end point in time. So space does get consumed because the new track was written to a space on the back end. And if I had a linked target linked to this snapshot, and it was written to, it would behave the same way as the source did in this example. It would write its data to a new location on the back end. But the snapshots never change. They point to the original point in time capture of the source image. And we don't have to move any data. We don't stop the I/O, copy the data, reconnect to the I/O. It's all updated on the fly by moving these pointers around. Very, very space efficient. Can make many, many point-in-time copies with very little additional capacity. So what we did with this technology is build a solution called Data Protector for Z Systems, or ZDP for short. And what Data Protector for Z Systems did, when we introduced it in 2016, with many production customers using this, is it allows you to recover very rapidly from a logical corruption. Remember, I talked about how bad data written to an environment will dutifully get replicated very efficiently by the remote replication solutions and corrupt all copies of the data at your primary and remote sites. This solution will allow you to make these point-in-time copies at any site that you choose. It's often done at the DR site, but doesn't have to be. And you can recover from the logical corruption that was introduced by using these pointers, these pointer-based copies. So we allow you to snap. We tested up to 32,000 volumes across multiple frames with a frequency of every 5 minutes. So you can make up to 1,024 versions of every volume in the environment at a frequency as short as every 5 minutes. And we provide an ISPF and a batch interface to manage this solution. We basically built this because a customer wanted a point-in-time copy of his data, and he said, "I've been waiting 30 years for this. This is what I want to see you do with the SnapDX technology," and it was really a customer-driven initiative to build CDP. So let's take a look at what we're really seeing in the way customers typically use this. Most customer implementations, although not all, place this capability at the remote DR site by adding some additional capacity, often as little as 30%. We see sometimes 50% additional capacity to be able to make hundreds of point-in-time copies of this data at a frequency of every 5 or 10 minutes. So this kind of depicts the notion of remotely replicating a volume to many point-in-time, and creating many point-in-time copies at the remote site. And if a corruption occurs that affects the production environment, of course, it gets replicated. The corruption would be replicated, and perhaps some of these snapshots would catch that and also be corrupted. But there would be a most current good copy of the data certainly available, and that point-in-time copy could be used to restore the data back to the remote secondary and push the data back to the remote primary, the production site if that was required. So the idea here is to create an air gap, in a sense, what we call a virtual vault, because you've got this data that's not addressable directly, that's preserved, that's immutable in these snapshots. And by having a high frequency, short interval, you can get a very granular point-in-time copy that will minimize the recovery duration, because you got a point-in-time copy that's very close to the point of corruption, as opposed to reaching back to last night's backup of a volume, or if you're a big environment, maybe you'll do that every night, and then having to reconstitute it from a tape copy. You have the ability to just simply restore the data. So you have enough depth to discover the corruption, and you can, as we'll see, hold some highly frequent copies for a few days, but hold copies that you want to hold maybe one a day for 14 days, for example. All of this can be done with the ZDP solution, which automates this. The concept is, of course, that you take a certain amount of copies that you define, up to 1,024 of each volume. And when you go to create the 1,025th one, the oldest one expires. So this rolling snapshot capability is what ZDP provides. It manages the SnapDX technology under the covers to create this continuous replication, local replication, and continuous point-in-time copy solution. Now, if you want to ensure that some of your data cannot be deleted by the user interface, you have the ability to optionally make some of the data sets secure. So we have now two kinds of snapshots. We have standard snapshots and secure snapshots. So if you mark the snapshot secure, instead of having a time to live parameter and expiration date, it basically has a time to must live. The hardware enforces it. It will not allow the user interface to terminate a snapshot that has been marked with the secure feature. It really tries to provide additional protection against not only unintentional, but certainly intentional data loss. This might be the case in if you have a malicious actor, right, who may want to erode employees, who may want to delete the snaps. Can't be done on snapshots that are marked secure. They will eventually expire based on their expiration date, but if you need to delete a secure snapshot prior to an expiration date, you need to involve Dell services to do that. The user interface will not allow that. Now, the other attribute of secure snapshots is that it will actually hold onto the snapshot to the point where it will, if you had a severe space situation arise, you weren't paying attention to any of the messages that we issue, and you had a severe space consideration arise in the array, we will preserve secure snapshots to the point of not servicing host IO if they were taken on the primary side, or not servicing SRDF IO if they were taken on the remote secondary side, and sacrifice data access over on the altar of preservation of data. Secure snapshots will not be terminated in that case. If you have a severe space condition occur in the array, what the array will normally do with standard snapshots is terminate them to make space available for host IO so that we can preserve access to service host IO or SRDF IO if it was on the secondary side. That's the way a standard snapshot would behave. But if you say you want them secure, we will sacrifice host IO to ensure that that snapshot does not go away. So most customers actually use a mix of standard and secure snapshots because you wouldn't necessarily want to make all your snapshots secure in case you had this admittedly unusual condition that would not normally in a well-managed environment occur. But if it did occur, you would be able to preserve the data in secure snapshots. So how do we deploy this in the real world? Well, what we have customers doing very often is creating snaps every 10 minutes. That was our previous minimum. Our new minimum is 5 minutes. But a lot of customers went to creating them every 10 minutes and say, we'll make the one that's taken at the top of the hour marked as the secure snapshot. So that in the definition of ZDP, you can say, I want to skip so many, and then every nth one I want to be secure. So we'll say we'll make the one at the top of the hour secure. And the remaining snapshots are standard snap sets that can be created. So under ZDP control with 10-minute snaps, given the number of minutes in a day, that's 288 rolling 10-minute snaps, and you can create them. Very commonly, customers will hold 2 days worth of that. So that's 48 hours worth of 10-minute snaps, but it could be whatever the customer wants. And in this case, as I mentioned, they will be terminated under legitimate space issues. And you will have the ability to recover back to up to 2 days ago. But if you have a runaway activity or some malicious actor that overwrites the entire array, we'll be able to use the secure snapshots, the 1 per hour. Meaning there were 48 over 2 days. The 1 per hour that was secure, they would survive if you had such a malicious action that overwrote the entire array, which is a common question we get. What happens if someone overwrites the entire array maliciously? Secure snaps are a method to ensure that you have point-in-time copies available to you. So this concept of mixing secure and non-secure is very common. So this is a typical implementation of a two-site solution that is asynchronously replicated. And in this example, we're showing the 288 10-minute snaps over 2 days. And if you did the hourly secure snaps, it's common for customers to say, I want to keep 7 days of those. Some customers might keep 14, some might keep 30. But we have these point in times that are marked secure that you can intermix with this with the standard snaps. So the amount of capacity that gets consumed here is really a function of how many snaps are you taking and how long are you keeping them. If you're going to take a snap every 10 minutes, you're going to consume a little more capacity because you're capturing more unique points in time and preserving updates that were taken on a more frequent basis. So you're going to consume more capacity than if you were snapping once an hour. I think that kind of stands to reason. But the tuning of the sizing tools that we have, if you're a current PowerMax user, certainly could be used to not only estimate, but actually measure how much additional capacity you would need. And if you don't run on PowerMax today, we have other methods to estimate what the capacity required is. But it's, as I said, is extremely space efficient, and you can take multiple point-in-time copies with, we've seen as little as 30% and as much as 50 or 60%, depending upon the frequency of the snaps and the retention that you're keeping. But that's all can be analyzed using the tools that we offer to try and size the capacity requirements for our ZDP solution. Now, in addition to the secure attribute that you can put on snaps, we have this additional layer of security called two-actor security that ensures that two people are required to execute changes to the ZDP definitions. And in this example, we would say a storage admin might be one actor who would create the job that wants to modify these definitions, and maybe perhaps a security administration or some other higher level authority would authorize the execution of that. So when we have actually implemented this using PowerMax itself, the ability to turn on two-actor security is a setting in the array that only can be altered by Dell service personnel. So if that setting is made in the array in the service interface, then the ZDP solution will behave differently and will implement this two-actor security feature, which has been written by exploiting SAP facilities and setting up profiles that will allow this two-actor security method to be implemented using tokens that identify exactly what the job is supposed to do, creating a token based on its exact syntax. And if someone tries to alter that syntax, then that job will fail because there's been a token created that is a mirror and built out of the exact syntax used for the definition change job. So there's a capability here to ensure that two different people are involved the way it's implemented through our interface into SAF, and that's enforced through the ZDP two-actor security function, which is enabled by the PowerMax itself. So when ZDP comes up, it detects whether or not the PowerMax has asked for two-actor security, and it will go down this path that's been implemented through SAF and different X-Facility profiles to ensure the two-actor security is deployed. So this is a feature that was asked for by customers because they're concerned about the rogue employee or the employee under duress, right? We're trying to solve the coercion case here. This doesn't solve the collusion case. Two people could collude to do something, but we're trying to solve the coercion case or the rogue employee when this is implemented. In addition to the capabilities that ZDP provides itself, we also have an interface between our GDDR solution and ZDP called cyber protection automation. This example is showing a very robust 4-site solution that's managed by GDDR with 4 sites, 2 in each region, with the SRDF asynchronous replication between the regions. Region 1 on the left, DC1, DC2, region 2 on the right, DC3, DC4. And this solution is available for robust DR protection, providing a DR capability that also provides synchronous replication when you move to the other region. So this is probably our most sophisticated solution. But what I'm using here is an example of taking one of the copies, the DC4 copy, where a ZDP has been defined and is running against the DC4 copy, and having a separate physical vault introduced into the environment. So not only do I have the virtual vault that's in DC4, I introduce a different physical array. We're calling it CR1, and we are attaching that array to a point-in-time copy created in DC4 through a snap set creation created by the ZDP running in DC4, running against DC4. And that snapshot is made to a SRDF primary R1 volume, this orange R1 volume, and it sends the data over to its partner, R2 volume in the vault. And then there's a ZDP defined in the vault that is cycling and creating point-in-time copies at a different frequency and holding them for a different duration. And if you want that vault to be air-gapped, we have an air-gap management server capability that will run in the vault and open and close that SRDF connection between those 2 orange volumes so that it is a physically isolated vault. We are starting to see the emergence of physical isolation being required in mainframe environments. It's more popular in the distributed world, but it is showing up in the mainframe world. We do have some deployments now where a physically separate vault that is also air-gapped from a connectivity point of view is being required. So our cyber protection automation solution as a feature of GDDR kind of works with ZDP to create point-in-time copies in a virtual vault and also in a physical vault. So this is another deployment option for ZDP. So in summary, what ZDP is doing is providing a host-based automation solution that creates these snapshots on a regular basis. It drives SnapVX. It can create a logical air gap through GDDR's cyber protection automation feature, and it gives you the ability to rapidly recover from point-in-time copies of data if you had a pervasive logical corruption issue. And if you've been in environments where there's been pervasive corruption across a large amount of data, particularly DB2 tables that are interrelated, as an example, I've been on crit-sit calls that have lasted for a long time trying to recover a large DB2 environment where hundreds of tables have been corrupted. You might find it faster to go back to a prior point-in-time copy, restart the environment, and chase as little log data as possible to reconstitute the environment. So it's another solution that the storage array can provide to speed up recovery because you get a point-in-time copy that's close to the point of corruption. And as we said, it can make up to 1,024 copies of each volume. and allow you to make some of these snapshots secure to guarantee the availability of the data, and will automatically roll off the older snapshots. And it is scalable. The largest environment we have, we'll talk about one example here that has 27,000 volumes across 4 arrays, replicated in a 4-site topology that is taking snaps every 10 minutes. So it can scale quite wide. And if you need to create a separate physical vault, we have the ability to support that as well through our GDDR cyber protection automation feature. So let's switch gears a little bit, talk about resiliency for both disk and tape. I just want to have a brief mention here of what we offer when we combine our tape solutions and our disk solutions. So what we see our customers choosing is in the PowerMax environment for DASD. In our experience, the most common choice is intervals measured in minutes, maybe 10 to 15 minute intervals, perhaps up to an hour, some at 30 minutes, and keeping that data for 7 days. This 2 or 3 or 4 a day is not the most common implementation we have. We do have some doing that, to be fair, where they take it at 2, 4, 6 hour intervals. And some customers do that actually on both sides of the array. So it's really up to what the customer requirements are, but it's very common to hold some number of snaps for a 7-day period. But in our experience, customers are exploiting the capability for high frequency and doing snapshots in less than an hour between snap. 10 minutes, 15 minutes is rather common. But we have the ability to do both. Now, in our disk library for mainframe solution on the tape side, we see customers taking snaps in 12 to 24 hour intervals of their tape environment and keeping those for anywhere from 30 to up to 100 days. Most commonly, it's a 24-hour interval. So the retention periods are longer in tape. 30 days is common, and the frequency is much more coarse, typically at 24 hours. So let's take a look at how that might be implemented using our disk library for mainframe in concert with our DASD solution, or actually independently. We do have some customers that have disk library for mainframe and do not have PowerMax as their DASD vendor. So that can be done as well. Of course, isolation is very common when we see tape solutions with physical isolation requirements. I'm often discussing with customers, mainframe customers, who've been asked to physically isolate their vault because their open systems or distributed brethren have implemented that in the past, and they are being asked to paint the mainframe DR or cyber recovery solution, I should say, with the open systems brush, which says we want to have a physically isolated vault. And if those are the policies that the company decides to choose, then we can certainly accommodate that and have the ability to make a isolated vault to hold either the DASD or the tape or both. And this library for mainframe has this notion of a snapshot capability with the Power Protect, formerly data domain backend, where you can snapshot the entire tape library and also retention lock it, hold it for a specific period of time. You can use that for test purposes for your tape environment, or also as a recovery point, and make as many of those snapshots as you require. If you're also using PowerMax DASD, you can do the similar functions with ZDP that I talked about, and conduct basically any sort of recovery from this physical vault that you find necessary, either selective recovery, specific tape data sets or volume backups that are done on tape could be done here, or a wholesale catastrophic recovery of the entire environment. We do have a customer who uses our DLM to restore the entire environment from backups that were sent to the DLM, full disk volumes that represent the entire environment. So we have a customer that's actually doing that using DLM. You can also, in the vault environment, inspect the data or validate either the DASD or the tape snaps, and apply a myriad of tools, many of them from IBM, others from other vendors. Integrity, file integrity monitoring is a good example of a product that might be used here, or any of the third-party IMS or DB2 tools could be used to look at the data and conduct test recoveries or validate the data. So all of this activity in the cyber vault is made possible by making these point-in-time copies. It doesn't have to be a physically isolated vault, but when it comes to tape, oftentimes that's the requirement. If you have disk library for mainframe, you can also share the data domain that's behind it with the open systems environment, and have a physically separate cyber vault for both the distributed side and the mainframe side on the same tape infrastructure, virtual tape infrastructure, using DLM for the mainframe with a data domain or PowerProtect backend, and the same on the open systems using PowerProtect or the data domain solution, as it was previously called, to make the point-in-time copy in the vault through retention locking. And there's a cyber recovery server. And I just noticed I misspelled recovery. I'll fix that. The cyber recovery server runs in the vault to open and close the vault connectivity and create the retention lock snapshots in the tape infrastructure. So that's a solution that we offer today. Let's talk about some examples of ZDP and how customers have actually used it. Here's a large customer, actually the customer that implemented ZDP first. This is a 4-site topology with the synchronous replication region 1 across the top and the asynchronous targets region 2 across the bottom. In this environment, they run auto swap for continuous availability. And they use the region 2 DC3 site as the site for the ZDP snaps, where they take snaps every 5 minutes. Every other snap is secure. So there's 950 snap sets being taken, with every other one secure. And that's across 4 arrays. So they're replicating 4 arrays. There's 4 arrays in each site. And they take 20 snapshots per hour and hold them and keep 950 snaps total, and then rotate them off. So that's done on about 9,000 volumes per frame, so around 27,000 volumes in the single ZDP instance. We call that a versioned data group. That is the element that is started and stopped and manages the definition of the volumes. We call it a VDG, a versioned data group. And the VDG, in this case, is 27,000 volumes across 4 arrays. In addition, they take a once-a-day snap and mark it secure on the synchronous target up in DC2 in region 1 in the upper right, so that they have copies in both regions. So it's very common for customers to have this ZDP capability running in 2 different sites. Oftentimes the frequency would be different. Maybe they're offset from each other, but they have the ability, of course, to create a VDG in any environment they like, and they can run that VDG locally or run it remotely. It just runs on a ZOS host that has either RDF or FICON connectivity to the arrays. Here's another example. This is a securities industry example. This is a 4-site topology with 1 array in each site. And they take 2 snapshots a day at the synchronous target in the bottom left. And in DC3, one of the asynchronous targets, they're doing 30-minute snaps with every other snap marked secure. And then they also do some manual batch SnapVX batch job captures of individual volumes on a daily basis, and then they hold those for a year. So there's a couple of different ways you can do it. This customer is doing it with a mix of ZDP and the SnapVX batch utility. But again, another 4-site environment example. This is a 2-site environment example. This is a brokerage customer with 7,000 volumes in each frame, so 21,000 volumes per site, because there's three frames. It's basically a 2-site asynchronous replication solution. And in GDDR, we call that DC1 and DC3. DC3 is an asynchronous target. And the production DR site is a DC3 SRDFA connected. And they also have a vault array that is also SRDFA connected in the primary site as a dedicated cyber vault array. And it's physically located right next to the production arrays. And they snap those that SRDFA secondary in the DC1 site and the bottom left. They snap that every 10 minutes and hold it for a day. And that is their catastrophic recovery vault. That's the way they view it, right? What they call their bare metal vault. And they're snapping every 10 minutes there. Now, they also do regular site swaps, as most well-managed environments that do remote replication do. They will periodically, some under government requirements, move to the remote site and run there for a period of time. And when they do that, what they've been running with in a normal environment is they run what we call adaptive copy, just to keep the vault array in the remote site at the right side of the screen pretty current. And when they swap sites, they will swap or switch that SRDFA adaptive copy into a normal SRDFA connection. So they'll go from adaptive copy to SRDFA, and they will do it in the DC3 region what they were doing in the DC1 before, after having done a site swap. So they'll just switch between these two sites, and whichever site is the production environment, that's the site that will have the cyber vault array copy with a snap being made every 10 minutes of the entire environment. Again, 21,000 lines in the versioned data group definition here. So this obviously can scale very well, and they've been running this for several years. Here's another example with this kind as a state government, two-site SRDFA with snaps being done on both sides of the environment. We have several government accounts that do this. This is a state government account, two-site asynchronous. This is a smaller environment, but they snap hourly, and they snap on both sides of the SRDFA link. So they have they have two cyber recovery copies, one in each data center. Here's a U.S. federal government agency that's quite large, 25,000 volumes per site, and they have multiple different sysplexes in this environment, 17 sysplexes, and they snap on both sides of their asynchronous replication relationship. In every sysplex environment, they have a VDG defined per sysplex, and they snap on a 6-hour interval on each side. So this is a good example of how you can have both belts and suspenders and make sure that you have recovery points in all data centers. So just some examples of how some customers are using ZDP. It's been around for some time now. So I think we've covered the ability to protect the data. I just want to make a few comments about restore. ZDP itself has a restore capability. You can restore the entire environment back to a prior point in time. There's a command, obviously SAF protected command, that allows you to do a restore. But we also have ISV partners that have recovery tools. Rocket Software did a presentation earlier in the week on their data recovery for Dell ZDP product, where they can do data set level recovery out of ZDP snaps that are created either locally or on a remote site. So if you missed that presentation, look for John Crosdale's presentation from earlier in the week from Rocket Software, where he describes that product function. Also, IBM for 21st Century IZBR has an ability to interface with ZDP to do more granular recovery or surgical recovery out of ZDP snaps. So recovery capabilities do exist today to recover the data and find the good data in the environment at a data set level. So you can do both data set level recovery, volume level recovery, and of course the entire environment. So the ability is there to do recovery operations within the product and with other vendor software as well. So that's protection and recovery. Let's take a look now at detect. So detect is what I call the holy grail of the cyber resiliency solution set. It's the most difficult to solve. It is not yet fully solved. It is where there's a lot of focus on the part of both software vendors and hardware vendors in this area to try and help customers detect whether or not they have a potential attack underway. And we have two ways to do this in the PowerMix. One's microcode based, and one's kind of a combination of host software and microcode. The first one is a product function called Cloud IQ. This was discussed in a couple of sessions in the storage track here this week. But what Cloud IQ does is has the ability for both open systems and mainframe environments that have compression enabled. And of course, PowerMax has the ability to compress CKD data. And if there is a detection by the PowerMax array that the amount of unreducible data, the loss of compressibility within the array has been detected, as shown in this red circle, as time marches on here, we're seeing that the amount of unreducible data grew dramatically from 15 gigabytes of data being unreducible to 65 gigabytes of data being unreducible in this interval. That something happened to make the data unreducible, which could be, of course, an encryption. And if there is a rogue encryption going on, you might see a dramatic drop in the unreducibility of the data. And if that happens, there is an alert that's issued by Cloud IQ. This applies to CKD data as well as an anomaly, right? This is one of several anomalies that Cloud IQ can detect, but it's a compression anomaly that says, look, we can't reduce this data anymore. You should have a look at this. Why is this all of a sudden the case? We've had this large spike in the amount of unreducible data. So anomaly detection, this is available in the PowerMax 2500, 8500, and it's basically a microcode-based function. So that's one area of detection that we are doing that's in the storage array. And encryption is a typical cyber attack method to, of course, ransom the data, and we can detect that, then we can alert you to that fact when it's happening. Now, separately, we have released in October of last year a product function called Cyber Intrusion Detection for Z Systems, or ZCID. And what is ZCID doing? It's a host-based function that exploits microcode capabilities that we have in the PowerMax to determine and help you determine what is the working set size of data in your environment. And it can determines the working set size by establishing what is the access rate of the data. How many unique tracks are being touched in an interval of time against this SMS group, this device, or this data set, and help you determine what is normal for your environment in terms of its access rate. And what it will do is give you the ability to determine that and then set rules that will alert you if that access rate has risen beyond a certain threshold. So it's unusual access rate detection is what we're trying to do. The working name of this product was atypical access rate detection, AARD. You'll actually see that in the program name. We're trying to use the unique track access rate. How many unique tracks have been touched? We'll measure that and help you establish what's normal. And if it's something is accessed outside the norm in an unusual way, we will issue a message to the console, syslog, saying, look, the access rate is normally this, and it's gone over the threshold that you set. And maybe you should look at that. We're just basically trying to send up a flare and say, hey, look, someone's accessing your data in an unusual way. Now, note that this is not I/O rate, right? This is something that the storage array can provide, and then uniquely to the storage array, the ability to provide this. It's how many tracks are touched, either for read or for write, or for both, during a particular intervals in time at the data set or the volume or the SMS group level. So it's really trying to show you what is the normal access pattern for your data. And that's not something that you can get from I/O rate, because I/O rate is just the number of IOs, right? How many unique tracks are touched? If all of a sudden you see your master file being accessed from top to bottom at a time of day or a day of week that's not normally done, that's something you might want to know about. And we will alert you to those facts by you having written rules that say, if this is what I normally expect to see, and since we're continually monitoring against those rules every hour, every half hour, whatever interval you set, when we see the access rate has gone beyond what's normal, we will write a message to the console that says, yeah, here was the access rate that we observed. Here's the rule that you set. It has gone beyond that. So this can detect data exfiltration. If you set it up for read, it can detect encryption or corruption. If you set it for write, if the access rate is abnormal, beyond what you normally see during your normal business cycle. So in this little picture here, this is actually a customer environment where we're showing an SMS group over several days, and we see its access patterns approaching 200 unique tracks touched per second in an hour interval. These are hour-long intervals that we're showing here. This is the graphing capability that comes with the tool. And you can see there's definitely a visible pattern here. And the tool helps you through reports or through these graphical interfaces or through a CSV file that we will cut for you, and you can put it into Excel or SAS and analyze the data yourself. What is the normal access pattern? And then write rules. So in this example, a rule might be, if it exceeds more than 200 for an access rate, tell me. And certainly the highlighted thing in yellow there shows that it did exceed it, and we want to be told, because that's something we normally did not see it for that time of day. So it's pretty straightforward conceptually what we're doing here, but there's a lot of work under the covers to collect the data from the PowerMax, analyze it, produce a report, and continually monitor the data on an ongoing basis. So ZCID is meant to be run as a long-running batch job or as a started task. Once you've established the environment and what the rules should be, it'll run and alert the data with data access rates being beyond the norm. So that's cyber intrusion detection for these systems. So just in summary, we believe that recovery from logical corruption is the next and necessary wave of business continuity planning. We're going to be spending a lot of time in this space as customers start to adopt it and we develop new technologies here. It's a very exciting time to be in business continuity planning because this is a new, not yet fully solved problem. And we have to keep focus on the fact that either operational errors or malicious attacks are real threats, right? They've always been, operational errors have always been threats, but malicious attacks are even more so. And we need to find ways to preserve data integrity and availability beyond disaster recovery, because disaster recovery solutions do not solve this problem. And we really need to be organized around this, develop threat response mechanisms to help with the recovery, or more importantly, to help with the prevention or the detection. So that's where a lot of focus is. Our solution to the storage array certainly helps with the recovery, no question about that. You need the recovery capability in case this happens. It's very important. But we also need to focus on as an industry, on the other pillars of the NIST framework and develop tools and procedures that can exploit the storage array capabilities in this area. I think it's going to be a combination of various vendors and technologies that solve this problem. Storage has a role to play, certainly the recovery, but also, as you've seen, the detection. And I think you'll see this from this technology emerging as we go forward to try and build robust cyber recovery solutions and cyber resiliency capabilities in customer environments. So that's what I have. If you have feedback, we'd love to hear it. Thoughts or comments on the presentation or the content or questions, we'll be glad to take them as well. Any questions? I didn't hear anybody interrupt during the presentation, so I'll be happy to take questions now if there are.
There's nothing in the chat, Brett.
Okay. Well, I want to thank everybody for participating, and those of you that listened on the recording, thank you for listening. And if you have any questions, you know how to reach us.
Okay. Before everybody goes, the next session on the storage stream is at 1:30 with Gary Smoke doing a live demo with ZDP that Brett has fantastically presented on. During Brett's presentation, Gary Smoke's been pinging me saying that there's a problem with the lab environment over in Boston, and the lab for the ZDP demo is not possible. So what we're going to do, there will be no session at 1:30. So I'll log on at 1:30 and tell everybody the session's been cancelled. But what Gary has promised to do is to record a video of the demo once he gets it up and working again. And we'll put that back on the agenda so people can watch the video of the live demo. So apologies for that. But you know what? It's that tomorrow's world syndrome where live demos always cause a problem. So the next session for the storage stream will be at 3 p.m. UK time. A roadmap to leverage object storage with Glenn Wilcott. So apologize for the cancellation of the demo, but we will get that video uploaded to the virtual conference streams, so you can watch it later on. Thank you again, Brett, for a great presentation. And thank you, everybody else. Cheers.
Thank you. Bye-bye.
Bye-bye.